All right, now let's talk a little bit about buffers. You should have had an introduction to buffers in Chem 106. So, and hopefully in other classes as well. So this should be a little bit of a review. But we do want to have an understanding of how buffers work. If you add 0.1 molar concentrated acid to water, the pH changes from 7 to 3. If you add, 0.1 milliliter of concentrated acid. If you add 100 microliters, same amount of this HCl, to a solution of 0.1 molar sodium acetate and 0.1 molar acetic acid, the pH doesn't change at all or significantly. So why is this? What's going on? Well, when I have a solution of acetic acid, this is acetic acid here, it is a weak acid and it's going to dissociate into its acid form and the acetate ion, its conjugate base, right? If I can include in my solution not just the weak acid, but some of that conjugate base is also going to behave as a base, take protons from water, and create acetic acid. And so you have these two driving forces that are set up, ready to absorb any addition of hydrogen ion, in the case of adding a little bit of hydrochloric acid, but it can also absorb any hydroxide ion that you add. And so this is what we call a buffer. It's a solution of a weak acid and its conjugate base. The weak acid you can get generally because it's just an acid you can use. So this is an example of acetic acid. And you can get some of the conjugate base from a sodium salt of that conjugate base. So sodium acetate, for example. Okay. You can also get an amount of a weak acid in the form of a polyprotic acid, or an acid salt, we call it. So, for example, a combination that is typical is making a phosphate buffer. And when we make a phosphate buffer, we can add NaH2PO4, and if I think about the conjugate base of H2PO4, that's HPO4, and so I can add some of that, and I can add Na2HPO4. So here I would have an acid, and there is its conjugate base. Neither of these were in their acidic form. These are both kind of considered acid salts, we call them. But the result is you're going to have H2PO4 minus in solution and HPO4 2 minus in solution. The HPO4 minus is, we've already talked about the equilibrium that they undergo, right? It's going to want to both take and give a proton to form H3PO4, and that proton is going to come from water, or it can H2PO4 give a proton to form HPO4 2 minus, this is a 1 minus, and a hydrogen ion. Okay, so you have weak acids and a significant concentration of a weak acid and a significant concentration of its conjugate base. Okay, so whenever you have this, you have a buffer, right? You have a system that's ready to take hydrogen ions. The conjugate base will take the hydrogen ions, and ready to take the hydroxide ions. The acid will consume the hydroxide ions and result in more of the conjugate base. Okay, so there's a nice relationship between the pH and what we call the pKa of the weak acid. So Ka is the weak acid, and we know what the pKa is just taking the negative log of the Ka. All right. Now let's have a little discussion about what Ka means. Ka, or K anything, right, is always pKa. Let's have a little conversation about the pKa. pKa, or P anything, like in the case of pH, right? If I have pH, that means the negative log of the hydrogen ion concentration. And again, that's molar hydrogen ion concentration. That is the pH, right? POH negative log of the OH ion concentration. So pKa is the negative log of the Ka. And what the pKa ends up being is it becomes a special pH. It's the pH at which, so usually this is the Ka for a given acid. Let's say we're talking about our acetic acid, CH3COOH. There's our acetic acid. It dissociates to form H plus ion and CH3COO minus. Okay? This is in equilibrium. There's a K here. This is called a Ka because this is acid dissociation, right? If I take the negative log of that, I get the pKa. And the resulting value is a special pH. And in this case, the pKa of acetic acid is 4.76. The Ka here is 1.75 times 10 to the minus 5. pKa is 4.76. So that's a special pH. Ladder diagrams were introduced. I didn't talk much about ladder diagram at all about ladder diagrams. We have a homework assignment where you're supposed to kind of review it. And this is where kind of your ladder diagrams, really it's just a diagram for you to kind of get a conception of what's going on. So it's helpful here because for the case of acetic acid, at 4.76, that's a special pH. It's the pH in which the concentration of the associated form, the CH3COOH, is equal to the concentration of the dissociated form, CH3COO minus. And then as you go down in pH, so if the pH is 4.76 in a solution of acetic acid, you know you have equal concentrations of those two species. If I go down in pH, how are things going to change? How does the hydrogen ion concentration change as you go down in pH?
More hydrogen ion concentration.
All right. And if I have more hydrogen ion concentration, how is Le Chatelier's principle going to be applied here?
More hydrogen means it's going to shift to the left.
That's right. So if I go down, for example, to 3.76, at 3.76, there's going to be 100 times, or 10 times, more CH3COOH as there is CH3COO minus. Okay? So now there's 10 times as much of this compared to that. Here, it's a one-to-one concentration at that special pH. And as I go down each unit of pH, then I get 100,000, 10,000, right, and so forth. If I go this way, right, what's going to happen?
The hydroxide ion concentration increases, and therefore how does the hydroxide ion concentration influence that reaction?
This equilibrium? Good question. Well, the hydroxide ion concentration is going to consume this hydrogen. So it's essentially consuming a product, so the reaction is going to move towards, the equilibrium is going to shift towards the right. And I'm going to get 10 times more of this at pH 5.76 than that material there. Okay, very good. So, a little use of our ladder diagrams and also an understanding of what the pKa is. Now, the pH will equal the pKa if the log of this ratio here, the dissociated form over the concentration of the dissociated form over the concentration of the associated form. If these concentrations are the same, the log of 1 is, do you remember what the log of 1 is?
Nope.
Take your calculator, put it in your calculator.
Okay, I'll do that.
What was it?
It's 0. Or it's 0, yeah.
Okay, very good. So, log of, let me turn on my viewer so you can see my calculator. Log of 1 is 0. So, that means that this term drops out. So the pH will equal the pKa when these concentrations are the same. This is also a nice equation because you can predict what the pH will be based on given concentrations of either your dissociated or your associated form. This is called the Henderson-Hasselbalch equation, and that name hasn't gone away yet. I don't see them reference that name in the text here, but people still call it the Henderson-Hasselbalch equation, so you should kind of remember that name. All right. You might also think of it as the buffer equation. All right. So let's see. We can also use a systematic approach to the solution of buffer problems, where we again get multiple K expressions and the appropriate mass and charge balances necessary to get the number of the number of variables equal to the number of equations, right? And finally, we are going to substitute equations into each other until we get one that looks reasonably solvable, all right? And this, oh, good, it does reference the Henderson-Hasselbalch equation down here. So we can use the concentration of our dissociated and the concentration of our associated form. Here, the dissociated form is shown as the acid salt. Okay, very good. So let's see. Calculate the pH of a buffer that's 0.2 molar ammonia and 0.03 molar ammonium chloride. And then what's the pH after we add 10 milliliters of 0.1 molar sodium hydroxide? Well, we need to find, we're going to use the Henderson-Hasselbalch equation, and we need to know the pKa of this pair. All right? Now, I call it this pair because pKa is of an acid. And so we're going to have to search that, and we'll find it, but we have to make sure we search for the acid dissociation constant of the acid. Which one of these is the acid?
Well, it says right there NH4.
Okay. Now, if you didn't know that, what you have to do is compare NH3 to NH4. Think about the dissociation or the equilibrium between them, NH3 and NH4, right? Whoops. Let's try again. NH3 and NH4. Think about the equilibrium that exists there, right? And then you'll realize this has to be the H plus over here. And so which one of these is behaving as an acid?
The NH4 plus.
That's right. It's giving up the proton. Here, NH3 is taking the proton to form NH4. So that's how we'll remind ourselves that we need to find the equilibrium constant for the acid equilibrium dissociation constant for NH4 plus. So 5.7 times 10 to the minus 10. And then we take the negative log of that to get our pKa. So now we can solve for the pH by putting the pKa and adding the log of the ratio. 0.02 is our concentration of our NH3. 0.03 is the concentration of our NH4 plus. NH3 again is our NH3 is our dissociated form, and without the proton, and this one 0.03 is the associated form with the proton. Let me write down that equation here. pH equals pKa plus the log of, and the more generic form here is X minus, that's without the proton, and HX, or A minus and HA, right? So remember, this A, or the dissociated form, is always on top, and that's a positive value. You can flip this and make that a negative value, but we don't need to worry about that. So then our pH is 9.06, and the concentration of H3O plus ion, 10 to the negative 9.06, is 8.71 times 10 to the minus 10th. Concentration of hydroxide ion, 1.15 times 10 to the minus 5. And that is where we're going to stop. Okay, very good. They get a little bit more precise here by using the further use of this systematic solutions, right? But that is generally not where we're going to be spending most of our time. Okay, very good. Let's calculate the pH of a buffer that is 0.1 molar KH2PO4 and 0.05 molar Na2HPO4. All right. Oh, we skipped the second part over there. We'll do it for this one down here. Okay. What will our pH be? How do we do this one?
Let's see. Do we add the? We need the Henderson-Hasselbalch equation.
Yeah, that's right. The pH is going to be the pKa of our acid. Which one is our acid?
We got H2PO4 and HPO4, so it must be the H2PO4.
Very good. So let's go here to our appendix 11 and see if we can find for the H2PO4. That's phosphoric acid, so I'm going to go down to phosphoric acid here. There it is. And then go to H2. So the second one here is 6.32 times 10 to the minus 8th. And look, it even gives us our pKa of 7.199. See, this column is the pKa. So the pKa is 7.199. We're going to solve for the pH when our concentrations of our different species. Which one goes up on top here? Whoops, I'm writing, you can't see. Which one goes up on top here? So 7.199, that's our pKa. Which one goes on top here?
The top one is the dissociated form, which would be without the proton, so that's just the HPO4.
Very good, so 0.05, right? That's the molar concentration of the HPO4. And 0.1 is our concentration down here. Okay, so 0.05 divided by 0.01, that looks like it's going to be 0.5, right? So I take the log of 0.5, and that's the shift that's going to occur. So the pKa is 7.199, and then I add it to this value that I've solved there, so the pH is going to go down to 6.90 or 6.9. Okay. Very good. So that is the pH of our buffer. Now, what is the pH after we add 5 milliliters of 0.2 molar HCl to 1 liter of this buffer? Okay. How is the pH going to change?
Let's see. How do we do that?
Well, we look at the volume of the HCl that's added and the concentration of the HCl. And from that, we should be able to determine how many moles of HCl, because this is the moles of mole ratio. It's also molar ratio, but you can think of it as mole or molar, whatever's easier for you. And so what I want to do is I want to think about it in terms of moles of material here. So 0.2 moles for every liter times 0.005 liters, right? That's going to tell me how many moles of HCl. So 0.2 times 0.005 liters, it's going to be 0.001 moles of H plus ion are added. All right, and that is added to 0.1 liters. So if I divide that by 0.1, that tells me that the molar amount of H plus ion is 0.01. So 0.01 molar H plus ion. Now these are molar concentrations as well, can be used as moles or molar. So if I add 0.1 molar H plus ion, how is that going to affect these concentrations?
The top one is the dissociated.
That's right.
And the bottom one is the associated. So if you add H plus, I'm not quite sure.
Well, this here is the conjugate base of a weak acid, right? So if there's extra H plus ions, the conjugate base is going to take them up. So the concentration of this material, when it takes it up, it's going to become this, right? So the concentration of this material is going to decrease by 0.01. So instead of 0.05, it's going to be 0.04. And this one here, 0.1, is going to increase by the 0.01. So it's going to be 0.11. A new ratio here, 0.04 divided by 0.11. That is 0.363. Now I take the log of that, right? I need to take the log of that and add it to my 7.199. So log of that value negative 0.439, plus my 7.199. So now my pH is 6.75. Did my pH get more acidic or more basic?
Went from 6.9 to 6.75. It got more acidic.
Very good, more acidic. Is that consistent with adding a little bit of acid?
Yeah.
Okay, excellent. So we use the Henderson-Hasselbalch equation to identify the concentration of acids, or identify the pH of buffers, and it's related to the relative concentration of the conjugate base and the weak acid. And then we can also identify concentration changes based on shifts. Okay. Now, let's talk briefly about buffer capacity. Buffer capacity. This is the ability to prevent the change or a significant change in pH due to the amount of acid or base that we add. If you add way too much acid and then you convert all of your dissociated form to the acid form, and any extra acid that's added will change the pH because that hydrogen ion will just be around from the dissociation of the acid. On the same side, if you have a buffer and you add more base than the acid form can dissociate to consume, then the base will change the pH drastically as well. So the buffer capacity is how much you can add. And the buffer capacity will increase when you have more of your acid and conjugate base in solution. So buffer capacity is higher, 10 times higher for a 1 molar solution of conjugate or acid in its conjugate base, weak acid in its conjugate base, compared to a 0.1 molar concentration of a conjugate acid and its weak acid in its conjugate base. Okay, so there's a little review video that talks about this in terms of titrations, which I'm going to put a link on there for you to watch. Okay, good job. Now we want to talk about what we call activity effects. Activity effects. All right. If we add a little bit of sodium chloride, 0.1 molar sodium chloride, to water. So, for example, if I have 0.1 molar sodium chloride, what do you think the pH of that solution would be?
Well, I know that if you add like 0.1 molar sodium carbonate, it'll change the pH.
Okay, so let's talk about that. 0.1 molar sodium carbonate. Is that going to make the pH acidic or basic?
I think it's going to make it basic.
Okay, so why do you think that?
Well, because you get sodium ions and carbonate ions, and then the sodium ions, they don't do anything. But the carbonate ion, it is a conjugate base of a weak acid. So the carbonate ion is going to interact with water and form HCO3 minus, the bicarbonate ion, and release the hydroxide ion.
Okay, very good. And that is in equilibrium. And then we also know that the HCO3 minus ion will also interact with the water molecule and be in an equilibrium where we get H2CO3 and another unit of hydroxide ion, negative. So, yes, putting sodium carbonate into solution makes the solution basic because you're adding the sodium salt of a conjugate base, a weak conjugate, or the conjugate base of a weak acid. The sodium salt of the conjugate base of a weak acid. Okay? But how does that help us with understanding sodium chloride?
Yeah, the pH shouldn't change because sodium is the conjugate base of a strong base, conjugate acid of a strong base. Chloride is the conjugate base of a strong acid.
All right, so essentially you're saying that if sodium was to do anything with water, it would have to form sodium hydroxide and release the H plus ion.
Yeah, and that's not going to happen because sodium hydroxide is very soluble.
Very good. And the chloride ion, what would it have to do?
It would have to interact with water to form HCl, and that's not going to happen because the HCl is a strong acid. It doesn't come together.
Okay, so we would not expect a pH change when we add salt to water. However, we do get a slight pH change.
You do? Why?
Well, this is an interesting phenomena which we call activity. The activity changes, and we need to explain this activity by thinking about how much material is actually available. Okay, so for example, when I say that the pH of water is 7, what we're saying is the hydrogen ion concentration is 10 to the minus 7. Therefore, the hydroxide ion concentration is 10 to the minus 7. Even if those solutions are 10 to the minus 7 in terms of the amount of material that you have available in there, that material will not stay that way. Much of it will get complexed or kind of crowded or surrounded, and it won't be what we say is active. It won't be in its active form. Okay? The same thing happens with sodium chloride. If you put sodium chloride in water, the sodium chloride dissolves and you get sodium ions and chloride ions in water. That's not surprising. But if you put too much sodium chloride in water, eventually what happens?
Well, it forms a pile on the bottom.
That's right. So I have my sodium chloride that I'm putting into water, and more sodium chloride dissolves until we see a pile of it gathered at the bottom because the water has it's no longer able to ion or to help the sodium chloride ionize, right, to dissociate each atom or ion of sodium and ion of chloride. So that's something that we're familiar with. Well, there's another phenomena that occurs. Even before you see the solid that builds up and piles up on the bottom, many of the sodium ions and the chloride ions are not in the form of the sodium ion and the chloride ion. They are complex together. They come together. Or they just form complex ions on the surface of other sodium ions, or on the surface of other chloride ions, or on the surface of other complexes. So you have some of this species, units like this, and then these can interact with either positive or negatively charged chloride ions and formed NaCl2 minus, which is aqueous. All right. And so then you get all of these different kinds of complex ions forming. And so then the concentration of Na and the concentration of Cl isn't equal to the amount of sodium chloride that was actually dissolved in solution. And now again, this isn't because of this pile. This is long after. This pile that would form would be long after all these different possible complexations would occur. And so we have to use a different word in terms of, instead of saying, what's the concentration of sodium ion and chloride ion in a 0.1 molar solution of sodium chloride? What's the concentration of sodium ion and chloride ion in a 0.1 molar? Well, you would say it's 0.1 molar. You got 0.1 molar sodium and 0.1 molar chloride ion. And that concentration it's a fine statement, but in reality, what we often want to know is not what the concentration you put in is, but what's the activity, we call it, the activity of the solution of the ions in solution. And the activity is different. It is essentially telling us how many sodium ions and chloride ions there are, their concentration, but their concentration will no longer be defined by how much sodium chloride I actually put into solution. Okay? So basically, we're using a way to take into account all of these different complex ions that form, or the complexity that occurs when you get very high concentrations of ions in solution. Now, the concentration of ions in solution we have a term for, which is called ionic strength. Ionic strength. And the ionic strength formula is this, where essentially you take the concentration of the ion times the charge of the ion, and you square that charge, and then you add up those values all together, so the concentration of all the ions times their charge squared, add them all up, and then you divide by 2. All right? So, if we look at this and take the concentration look at the ionic strength of 0.1 molar sodium chloride for a simple ionic compound, diatomic ionic diionic, right? 2 ions, sodium ion and chloride ion. 0.1 molar sodium chloride. The ionic strength, you have the sodium ion concentration times the square root of 1 plus the chloride ion times the square root of 1, and then you take the sum of all that and you divide by 2, and you get the same value as the concentration. So for simple solutions where you just have singly charged cation and singly charged anion, the concentration is the ionic strength. Here, when I make a 0.1 molar solution of sodium sulfate, well, I'm going to have the concentration of sodium is going to be twice as much. You see why?
0.1 molar sodium sulfate. Why do you get 0.2 molar sodium ion?
Okay, so let's show that really quick here, right? 0.1 molar Na2SO4. Na2 dissociates, and when it does, we get 2 sodium ions and 1 SO4 2 minus ion, right? So the concentration of sodium ions is twice as much.
Oh, yeah, okay, I see that.
Okay, so the concentration of sodium is 0.2 times this 1 squared. Concentration of the sulfate ion, 0.1, but I have the -2, which I square, which gives me a 4 here. So this is a 4 times 0.1, 0.4 plus 0.2, and then we take it in half, so it's 0.3. So when you have ionic compounds that have numbers more than one of certain ions or multiple charges, then it will change the ionic strength. Okay, and now again, we're concerned about this ionic strength because our activity of our species, now activity is a new term that we're introducing now, and it's essentially saying the actual concentration, right? We're trying to find the actual concentration of components in complex solutions. So the activity of actual concentration depends on this ionic strength, and so now we know how to find the ionic strength for a solution. And the activity coefficient, which is a value that goes in front of the concentration, the activity coefficient is a value that goes in front of the concentration to result in the activity. All right, the activity coefficient is related, your activity coefficient is related to your ionic strength. Okay, so for example, the activity of some analyte A is the concentration of A times its activity coefficient. The activity coefficient is a number which is, at 1 or less than 1, right? So it's a fractional number that's going to lower the relative activity of your concentration by multiplying it by the activity, or by the concentration of your analyte. If ionic strength is very low, then there's no problem in terms of forming multiple what do we call them? Complex ions. Therefore, the result is the activity coefficient is 1, and the concentration of the analyte then equals the activity. All right? So we have effects for all of the equations that we've ever used concentration in. We now think of the concentration of that species times its activity coefficient. All right? Now, you don't have to do this moving forward for the rest of your life, but whenever there are issues and you can't figure out why your signal is not related to the concentration, then you can always start thinking about activity and why the activity might shift or the signal might shift based on the activity. All right, so let's look at our relationship between our activity coefficients and our concentrations. Now, another parameter that we need to take into account is what we call the effective diameter of our ion. And as an ion gets smaller, right, it requires less water to kind of surround it. But as an ion gets larger, more water molecules can kind of surround and help support that ion. And that's really what we're kind of looking at here. Because again, when you put an ionic compound into water, the water molecules need to congregate around those ions to help them dissociate. And so if you have very large ions, then you have lots of ion or water that needs to aggregate there. If you have a +3 charge on iron, water wants to aggregate, but if it's the smaller it is, the fewer water molecules can aggregate. Okay, so there's also an interesting relationship between the solubility of salts and the size of the ions on those salts. If the size is too small, not enough water molecules can fit around to solubilize it. Okay, so we have this equation called the Debye-Huckel equation. And the Debye-Huckel equation allows us to get the activity for an analyte, for any ion that we're interested in, using the charge on that analyte and using the ionic strength and the hydration ion's effective diameter. All right, so we have the ability, that's alpha here, is the diameter of the ion that you're after. And we have the charge on your ion and the ionic strength. Now, that's nice, but there are also tables that can just give us activity coefficients for given ions at different ionic strengths. And instead of using the Debye-Huckel equation to identify what the activity is, we're just going to use the tables to identify what the activity for the equation or for a given solution is. Okay, so let me show you some of those tables. So this is a table that we would usually use to identify the activity for a given ion in solution. Okay, so for example, if we look at the hydrogen ion, all right, the hydrogen ion here, it has, this is its ionic radius, right, or ionic diameter. And you can see how as these are all our positive ones, as you change the diameter, getting smaller, then your activity becomes a larger number, especially if you move to a higher ionic strength. So we go from 0.86 down to 0.8, to a smaller number. All right, now what does that mean in terms of if the activity coefficient, 0.86, 0.83, 0.80, what does that mean?
Well, you said you take the activity coefficient times the concentration, and that's the actual concentration?
That's right. So as your ions in solution get smaller and smaller, more water is being utilized to, or less water can fit around them. And so they have to find other ways other than the water to satisfy their charges. Okay, And looking at a single ion going across from ionic strength 0.001 to 0.1, we see that again we're decreasing our activity coefficient as we get higher in concentration. All right, and that is because as you get higher amounts of ions, then there's less water available. So let's try to answer the initial problem that we had and find out what the pH would be at a 0.1 molar solution of sodium chloride. Okay, do you remember that problem?
Yeah, 0.1 molar solution of sodium chloride.
Yeah, so we wanted to know what the pH would be, if it would be affected at all. And we can use activities to answer that question now. Okay, so we're going to make this activity table, or this activity table you can find online as well, and any activity table. I'll let you guys find it online. I think that's better. But let's find out what the pH then would be. So the pH in 0.1 molar water, where's the hydrogen ion coming from?
Well, I don't know. Where is it coming from?
Well, remember, it's not coming from the sodium ion or the chloride ion, right? It's coming from the dissociation of water being shifted because of the activity, right? If you have pure water, then we know that this is going to be 1 times 10 to the minus 7, and this is going to be 1 times 10 to the minus 7 as well, right? And so the pH is 7, pOH is 7 as well. However, if you alter the activity of these solutions, and that's what happens when you get higher concentrations, right? So at 0.1 molar, the activity of the H plus ion is only 0.83. So my H plus ion concentration, 0.0 or 1 times 10 to the minus 7, right? 1 times 10 to the minus 7 has to be tamed by our activity coefficient, which is 0.83. The hydrogen ion's activity coefficient at this concentration of this ionic strength, 0.1, is 0.83. All right, so then 0.83 is our activity coefficient that goes in there, and then that will tell me my actual concentration of hydrogen ion. So 1 times 10 to the minus 7 times 0.83. That is our new hydrogen ion concentration, and if I take the negative log of that, then I get 7.08 or 7.1. All right. So it's not much of a change, but there is a change in the hydrogen ion concentration. Okay, good.